Three-dimensional surfaces can also be parameterized. When parameterizing a curve, we were able to do that with just one parameter, whether that be an R2 or an R3. But when we parameterize a surface, we're going to need two parameters. The possibilities for these two parameter values are going to make up a domain D, and these UV parameters are going to be plugged into parametric equations to give an output that is an XYZ vector pointing to an ordered triple on the surface. And we'll call that surface cap S. The possibilities for the U and V values that are the parameters are going to make up that domain region in some two-dimensional UV plane. So when we parameterize a surface, we have a two-dimensional domain that maps to a surface with three dependent variables, each of which is represented by a parametric equation. And similar to what we've seen before, that surface can be expressed as a vector-valued function, but we can also just focus in on the parametric equations themselves. We'll oftentimes see this 2D domain region in the, let's say, UV plane, graphed separately from the surface, and we think about an ordered pair that's in this UV domain region as a UV point, and that UV point would be plugged into the vector-valued function, which then has an output that is a vector that points to an ordered triple on the surface, where the x is a function of u and v, the y value is a function of u and v, and the z value is a function of u and v. So in this example, we have a surface that is being represented by this parametric vector function, and we want to see if the ordered triple p is on that surface. And then again, we'll take a look and see whether or not the ordered triple q is on that surface. So first let's look at p. If the ordered triple p is on the surface, then there's some domain element u and v that we could plug into those parametric equations, and they would have an output that is 4, -5, 1. The components of this vector function are the parametric equations for x, y, and z. So we're looking for the uv values that make the x parametric equation u plus v equal to the x component of the vector, which is 4. That same uv value needs to be plugged into the y parametric equation, which is u minus 2v, and have an output that is -5. That same uv domain element should be plugged into the z parametric equation and give an output that is the z value of 1. And now we just need to solve this system of equations. Now there are several ways to solve a system. I'm going to use elimination with the first equation and this third equation. Once I subtract 3 from both sides, I get u minus v is equal to -2. And when we combine these two using the elimination method, we see that the v's cancel out, and I get 2u is equal to 2, or u would be equal to 1. If u is equal to 1, then that means the value of v has to be 3. So we know that if uv is equal to 1, 3, that's going to work in these first two equations. Let's check to be sure that it works in the third. So we plug in 1 for u and 3 for v, and we see that that is -5. And therefore, if we were to plug 1, 3 into the vector function, we do get the ordered triple 4, -5, 1. So we can say, yes, point P is a point on that surface. Now we'll do the same thing for Q. If Q is a point on the surface, then there exists an ordered pair UV such that the x component is equal to the x coordinate of Q, which is 0. The y component of the vector function, which is u minus 2v, would be equal to the y coordinate of the ordered triple. And the z component of the vector function, 3 plus u minus v, would be equal to the z coordinate of the point. Again, we have another system of equations to solve. I'll do it in the same way, focusing on this first equation and the third equation. After subtracting 3 from both sides down here, we get u minus v is equal to +3. We use elimination again, add these two together to see that the v's cancel out, and we end up with 2u is equal to 3. Solving for u, we get u is 3/2. We can take that back up into either one of these first two equations. We'll go with the top one to see that if u is 3/2, then v must be equal to -3/2. So this is the domain element that satisfies the first two equations and maps them to the correct x and z coordinates. We just now need to check it in the y parametric equation to see if it goes to the right y value. So we plug in 3/2 for u and -3/2 for v, and that is not going to be 4. And since that's not equal to 4, we'll then say that the ordered triple Q is not on the surface.